Question 9. An electron with a mass of me is traveling at 0.8 c, 80% of the speed of light, when it strikes a stationary neutron and stops. Right? Conservation of momentum says that the neutron has to start moving. Find the speed of the neutron after the collision. Now there are two ways we could be asked to solve this question. We could be asked to find the relativistic mass and the relativistic momentum of the neutron. In that case, our equation would look something like this. Rest mass of the electron times its velocity over our factor, except here, instead of v, we'll have to have velocity of the electron, equals, and then the momentum of the neutron, which will look almost the same. It turns out that this is really annoying and hard to work out. But the question doesn't stop there. It says assume that the neutron does not reach very high speeds. This means that this whole factor at the bottom will be very close to 1, and we can forget about it. This equation is much simpler to solve. And as we'll see, because the neutron does not end up moving very fast, we'll end up with an answer that is very, very similar to the answer that we would have got had we had the denominator here. So, let's get started. So what we're trying to find here is Vn, right? So we want to make this the subject of the equation. We have another problem though. We don't know how to relate Mn to Me, because obviously we want an answer that's a solid number and not dependent on whatever these masses are. Luckily the question gives us the mass of a neutron, 1,800 times the mass of an electron. So substituting in our numbers, we have 0.8 c for the velocity of the electron, which we've substituted in the denominator as well. And we can see that the mass of a neutron, or at least the rest mass of a neutron, will be given by this number here, right? Now, we can see that the MEs are going to cancel out. Fantastic. So, simplifying that and making V the subject of the equation, we have 0.8 c over 1,800 times 0.6. So this will give us an answer in terms of c. We end up getting 0.0007 c. Now can you see what this bottom factor would become if we substituted in this number for our velocity? It's not going to be very high. You can do it on your calculator now if you like. I can tell you right away you'll get a number that is approximately 1. Dividing or multiplying this number by 1 is not going to change its value. It turns out that if you go to the number of significant figures that you can say that's accurate to, it'll end up being at least about 5. So you really don't need to worry about the denominator in this case. This is the reason why when we're talking about classical physics and collisions between cars or cricket balls or whatever, we don't worry about this denominator. At everyday speeds, this denominator is so close to 1 that even if you left it in, you would get pretty much the same answer. In fact, your experimental errors, that is, problems with measuring the distance or time of the moving object, are probably going to be bigger than the change that this factor would make.